Hi, this is Mr. Max with Sankofa Mathematics. So what I'm going to do here today, I'm going to do the magnitude of a vector, and I'm going to couple it with a few um, methods, primarily the theory of Pythagoras. Okay, and what we're going to do when we're actually talking about the magnitude or that length of a vector, we are talking about, for example, in this diagram here, we're talking about this distance of this line, the length of this line rather. All right, so you don't take your ruler, for example, and start measuring A to B. So what you do is we use Pythagoras, the theory of Pythagoras, where you are supposed to take the sum of the squares of the two shorter sides in order for you to find that distance there. And we are going to write the magnitude of vector A, maybe vector A with a line under, or vector A that is bolded, as the modulus of a vector like this with a small line under, or we're going to talk about vector AB, all right, with a line on top there or an arrow on top, and when you calculate the modulus or the magnitude of the vector, we put it into lines like this. Okay, so when you see this, it means you are finding, for example, this magnitude of this line. Right, so we use Pythagoras and it's very straightforward. So what you see here is, remember that as a column vector, you have got your 3 here to the right, that's positive, and the 4 upwards, that's also positive for the y direction. So when we use Pythagoras and want to find the modulus of the vector, so you just punch it in there. And here's the thing, ultimately it doesn't matter whether that value of x or y is negative, because anything that you square will always give you a positive result. All right, so that is going to be 5 units, for example, there. So let me bring in a simple question again. So the vector is now given like this, with a small a with a squiggly a with a line under, all right, sometimes with a squiggly thing here, or sometimes it's bolded, right? So it's the same procedure. So that distance from there, the x direction obviously is 2 because you go to the right. Then the y direction is like you're going 4 units down when you count those blocks. So when you use Pythagoras then, so you're going to have this 2 squared plus negative 4 squared. Again, as I said, it's not really necessary for you to write this negative 4, all right? Just 4 will do, but in any case, you will still get a positive result there. So what you end up with is 4.47. Obviously, I've rounded that answer. All right, so let me bring in an exercise here. So I've got vector P, which is negative 3, 2, vector Q, which is 1, negative 1, and vector R, which is negative 4, 1. So the first thing that we need to find is we need to find the modulus or the magnitude of vector P. All right, the length of that. All right, so we're going to use our formula for Pythagoras. So it's negative 3 whole squared plus 2 squared. Obviously, you take the square root. And once you do that, you arrive at nothing but 3.61 as an answer, or the square root of 13. Right, let us just take again our vectors as we have them here, and we're going to add vector P plus vector Q plus vector R. So basically you're going to add all the x components together and then all the y components together. So when I have negative 3 plus 1, that gives you negative 2, and negative 2 plus negative 4, that gives you negative 6. And then you have 2 plus negative 1, that is positive 1, and then positive 1 plus 1, that gives you 2. Ultimately, that is the answer for the sum of these vectors. So let's continue with that exercise. And what we have here is they are saying we're supposed to find as a single vector. So this is 10 here, which acts as a scalar quantity for vector Q, all right? And then the negative 2 here is a scalar for vector R. So once you punch that in, remember that scalar quantity multiply with each one of the elements or the components in the vector. All right, so you have got 10 times 1, that's positive 10, and 10 times negative 1, that gives you negative 10, for example. Then what I do, I change the minus to a plus, because I know that negative times negative gives you a positive 8, and negative 2 times 1 gives you a negative 2. Ultimately, you are only adding your 2x components. 10 plus 8 give you 18, and negative 10 plus negative 2 gives you negative 12. So there's a question C here. We say, without making any diagrams, you're supposed to explain why this 10q minus 2r is parallel to vector p. So when you look at vector p there, it's negative 3, 2. So there must be a scalar that you can pull out there. And you will realize that 18 negative 12 is the same as when you take out that negative 6. And because that is the case, therefore these vectors are definitely going to be parallel. All right, so in the diagram you'll see one is longer than the other one, but they all then are parallel and going in the same direction. Right, now a D part here, and here you have to be a bit careful. The A here is some unknown value, a number, the B is a number, and then that's a 5 there. All right, so we need to find the values of A and B. All right, so immediately when you are looking for two variables, unknown numbers, all right, then you are thinking of simultaneous equations. So what you do here is I bring my vector P, which is negative 3, 2. I bring my vector R, which is negative 4, 1. I let it equal to 5, Q, and then I bring my vector Q here. So I'm going to multiply the A with negative 3A here, the B with negative 4, and the 5 times 1. That gives me rise to my first equation. I'm going to do the same with A times 2, which is positive 2, and B times 1 is B, and 5 times negative 1 is negative 5. Once we are here, you should be able now to solve these two equations simultaneously. You can either decide to make the coefficients of A equal, or the coefficients of B equal, or you can substitute by making B the subject of the formula. The methodology is totally up to you. The bottom line is, once you have these two equations, you should be able to solve them no matter what method you use. So what I'm doing here is that I'm going to write my B here as a 4. So I'm going to multiply each term in my second equation by that 4. So that gives me 4 times 2A gives me 8A. And 4 times b gives me 4b, and 4 times negative 5 gives me negative 20. So I basically multiplied the whole equation by 4, or I quadrupled it. So now I'm going to bring my equation 1, because essentially anything you multiply by 1 just remains that. All right, so the reason that I'm adding these two equations here is because I want to eliminate my b's here. 4b plus minus 4b will definitely eliminate the b's, all right, or the terms containing the b's. And 8a plus negative 3a gives you 5a, because it's the same as 8a minus 3a. And minus 20 or negative 20, add 5, you get negative 15. Right, so that gives you the value of a, which is negative 3. So now that I have the value of a, I then substitute it in either equation 1 or 2, all right? I always use the original equations. Right, so when I substitute it, for example, into 2, it's totally up to you, right? You should eventually get that the value of b is 1. So what we're looking for was a is equal to negative 3 and b is equal to 1. So I'm going to give you some time for you to look at it and pause the video and before we go to the next question. Right, so let me talk about position vectors. Now, I spoke about position vectors in my earlier video on the first part of two-dimensional vectors. I'm going to do the third part where I'm going to deal with geometry, all right? Vector geometry, algebra. Okay, so this one is basically the introduction as we are doing our two-dimensional vectors. So we said that a vector describing a move from the origin is called a position vector. So all of them start from the origin, okay, and you can also write them as coordinates. So for example, the point 5, 6, all right, if you have to write it from O to A, it will be as a column vector 5, 6. And the point B from the origin will be negative 1, 4. Here it is as a coordinate, and here it is written as a column vector, obviously starting from the origin. So I'm going to do an example where I talk about that. So what you have when a vector starts from the origin, it's referred to as a position vector, and you always start with an O. Right. You also have free vectors, which basically start from any point. So you have your initial point and your terminal point. The initial point of a position vector is at the origin, all right, while the initial point of a free vector can be anywhere. So let us take a few examples. So if I bring point A here, and this is the origin that I have here, and I want you to write it as a position vector. So from the origin, so you count 1, 2, 3, that's why I have the 3 up there, and 1 up. All right, so if I bring another point from the origin here, you see I'm going -1 to the left and 2 up. So that is going to be -1, 2, all right, as a position vector. So let me bring one more. So to go from C, from the origin, you go 1 across and 1 down. So you have got 1 positive and 1 negative. And that is how basically you will be writing them, because they are starting from the origin. So you should be able to write them as a coordinate. The same, it will be 3, 1, or as a vector, is going to be 3, 1. Right, I'm not going to do a lot on base vectors because your syllabus for this particular part does not really require you to do that. But it's always interesting to know that we use I and J to refer to our column vectors. Now, when you do the alphabet, obviously I comes before J. The same as when you would be doing your Cartesian coordinate system. You know that the X comes before Y. So the I is the first one here on top, and the 3 here will refer to your J. So when you have a vector 2, 3, all right, and you're supposed to, that is a column vector, then the base vector is going to be written like that there. Right, so let us take just a small example where we are going to write the following as base vectors. So from C to D, so when you look at the position that you go, it's 1, 2, 3, 4 for I, and -2 down for J. So C to D will be 4I minus 2J. And when you do E to F, for example, now you do not have a movement in terms of your I, but you definitely have a downward movement in terms of your J, and that is -3. And lastly, if I bring one from G to H, when you count, it's 1, 2, 3, 4 for I, and 1 up for J. So that is, in a nutshell, how you will be writing those particular vectors there. All right, so don't mind my capital letters here, or the different form when you have a column vector 2, -1. The base vector then is the same as 2I minus J.